Welcome to the third experiment of EEE 342 Introduction to Communication Engineering Laboratory. In this experiment, we will talk about the sampling process, how we can convert a continuous signal into a sample signal or a discrete time signal. And in the report section, you will actually retrieve the original signal from the sample signal. So it's a two-step process. The first step is converting a continuous signal into a discrete signal or a sampled signal, and in the receiving end the sample signal is again converted to the continuous signal, and that's left for you to do in the report. So in the demonstration part, we will just convert a continuous signal into the sample signal or the discrete time signal. Prior to this video, I have already attached two videos from my theory course EEE 341, which covers the whole theoretical concepts of sampling process. Why is sampling necessary? What are the conditions of sampling? What components do we need for sampling? And what are needed for reconstruction as well. So if you have skipped those two videos, that is not a very good idea. I would recommend you to go back, watch those two videos. That will probably take you 20 minutes. And those are the concepts that are actually necessary for understanding this whole demonstration process. So go back and watch that video and come back. So I believe it's the third experiment, so you have already done homeworks on experiment 1 and 2, and you already know how to operate a Simulink, how to build a model, how to browse components from the browser library and all. So I'm not going into any unnecessary details. I am just directly hopping into the experiment. So let's go. So this is an experiment where we want to convert a continuous signal into a sampled signal. I have already said it in my theory videos that I have attached, that sampling essentially means multiplying a continuous signal with a pulse train or an impulse train. So just a little overview of what we are going to do. So yes, so as I have said, we have to multiply our continuous signal with the pulse train. So we need a continuous signal. For that purpose, we will use a sine source. So it's a sine source. You already know how to choose sine source from library browser. So you need a sine source, and you need a pulse train or impulse train, whatever you say, impulse train. This is a new component for this experiment. So let's say sine wave is something like this. You can adjust the frequency, you can adjust the amplitude, of course, and the impulse train is a set of impulse, something like this. So we need to multiply these, right? This multiplication is basically the sampling process, nothing else, just the multiplication. So for multiplying, we need a product block. We need a product block. You already have worked with product block, I suppose. So it's a familiar block again. And the output of this product block is actually the sample signal. So we will try to see it and visualize it in the scope. So we need the scope block as well. So only 4 blocks and the experiment is done. This is one of the most straightforward experiments. So nothing to worry or nothing to be afraid of here. Basically very simple. So we need these 4 blocks: sine source, which is already familiar, then impulse train, then product, and then scope. So let's get started. So here is our library simulator. So I'm gonna choose my sine source from this library browser. In the Simulink section, we have the sources. So let's choose our desired sinusoidal source from here. So here is our sine wave. You can just drag it from here to our blank screen. It will take some time. Okay, so our sine source is already here. So let's get back to the library browser. Okay, so we will just set the parameters later. So don't just leave it as it is. Just maybe we can drag it here. Okay. Then let's get back to the library browser, and we will get the pulse train from these sources as well. The pulse train is here, pulse generator. You can just again drag it. Okay. Done. We will just set the parameters later. So pulse train and sinusoidal block, as I have said in my overview. So that's all. Okay. So now we need to adjust the parameters. So let's adjust them. Just double clicking it will do. The amplitude, let's say the amplitude is 5 volts. You can choose whatever you want. 5 volts. No bias, of course. Now the frequency, it's important. I have mentioned this in detail in my explanation videos, that when we are sampling a signal for perfect reconstruction, we need to obey the Nyquist theorem. So the sampling frequency or the frequency of the pulse train must be at least twice the original signal of frequency, right? So let's take our original signal frequency as 500 Hertz. It is also mentioned in the lab sheet. So our original signal frequency should be 500 Hertz. You can choose any frequency you want, but you have to make sure that you are obeying the sampling theorem or the Nyquist theorem, right? So let's do a 500 Hertz frequency. Now 500 is frequency in Hertz unit, but we need in radian per second unit, so we need to multiply this with 2 pi. So 500 into 2 pi is basically 500 multiplied by 2 multiplied by pi. So that's all. No phase, of course, it's a sine wave. If you want a cos wave, then you can add some phase shift here, pi by 2. Then sampling time. Sampling time is actually how many samples do you need, let's say per period. So you can just put a small value here, let's say 0.00001. Okay, that's done. So let's see if our sine wave is working well. So okay, and we want a scope too. So let's bring a scope here. In the sync section, you will get the scope. Let's bring a scope here. We will at first use this scope to visualize this sine wave, if it is okay or not. Let's check. Okay, so simulation. Oh my god, I have made a mistake. Okay, simulation is done. So the mistake I was talking about, I haven't set the time axis for the scope. That's a big mistake. So let's adjust that. One thing, our frequency is 500 Hertz. So if you consider the time period is 1 by 500. So you need to adjust the timing of the scope accordingly, right? Without adjusting the timing of the scope, you will not get the proper visualization of your signal. So for my case, my time period is 0.002 seconds. So if I want one period, I will set the time to 0.002. So let's see how does that work. Again, I am simulating. This will simulate very fast because my time frame is very short. Let's check. So here we are getting one complete cycle. You can see some jagged edges here. That is because of the sampling time. You can adjust it a bit more. Here sample time, you can reduce this a bit so that you get rid of the jagged edges. So a bit more precision. Again, if you simulate it, you can expect a much smoother curve. Now we don't want one single wave. Let's say we want five full waves. So just multiply this time with 5. It will be 0.01. So we can expect 5 full waves now. Okay, so here it is, our 5 full waves. I'm not happy with the jagged edges, so I might want to reduce the sample time a bit more. I want to take more samples, so I'm just reducing it by 10 more times. Let's see how does that work. Okay, so now I'm happy with it. It's much smoother. Let's not get too fussy. Let's move on. Okay, So that's all for the sine source. Now we want to adjust our pulse train as well. So let's get to the pulse train. Now for the pulse train, amplitude is 1 because we want all the impulses to have amplitude of 1. Now the period is important. Period is important. As we have said, we have to follow the Nyquist theorem. So the sampling frequency must be at least double of the original signal frequency. Original signal frequency was 500 Hz. So our time period was 0.002. Our the pulse generator should have at least twice of the frequency of the original signal. So it should be at least 1000 Hz. If not more, it should be at least 1000 Hz. So for 1000 Hz, our time period is 0.001 seconds. 0.001 seconds. So I am just putting 0.001. If you want more precision, you have to, let's say you want to increase your frequency to 2000 Hz. It's fine because 2000 is greater than double of the original signal frequency, which was 500, right? So 2000 is also okay. But if you want 2000 Hz, then your time period should be 0.0005. So if you want more precision, if you want more samples, then you want to reduce the period, right? You want to reduce the period. Let's say it's 0.001 at most. If you want to obey the Nyquist theorem, 0.001 is the highest limit of the period. If you want more precision, you can just reduce this by doing this. Otherwise, we want to go with 1000 Hz, so 0.001 is fine. Now, pulse width. I have already talked about two types of sampling. One is ideal sampling, another one is natural sampling. In the case of ideal sampling, you know, all the pulses were actually perfect impulses. But in the case of natural sampling, the pulses were not totally impulse. They were actually rectangular pulses, right? It had a short time window where it was high and then an interval when it was low and then again it was high for a short time. This pulse width is actually the percent of the period, how many percent of the total period you want your signal to be high. We want it as close possible to a impulse train, so we want to keep it just an impulse. So if my time period is 100%, I might want my impulse to be high for only 1% or 0.1%. 0.1%. 0.1%. Not put it in that. Let's see how it turns out. So just save that. Okay. Now we want to check our impulse train with this scope. We don't want another scope. Okay. So let's just simulate this. You can see our time period of this impulse generator is 0.001 and our time frame for the scope is 0.01. So it's 10 times of the period, so we can expect 10 impulses. So let's see. Here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 impulses altogether. These are actually very close to impulses. You can see very thin lines just like impulse. 1 in that particular time and 0 otherwise. If you want more precision here, you can just reduce the percentage. You can say it's 0.01%, then it will be much thinner. Let's say if our naked eye can actually catch that. Simulate it once again and in the scope. Not much improvement because our eyes have some limitations, so we cannot actually visualize this decrement in the width. So 0.001 is fine for impulses. Let's do a bit more percent. Let's say we are having a 5% here. Now what will happen? We will not have impulses. Let's see. Yes, you can see that this time this pulse, every pulse has a visible width. It is not as narrow as it was in the previous case. We will use this type of pulses when we want natural sampling, and we will use very small percentage when we want actually ideal sampling. So we are doing ideal sampling at first, so let's reduce the percentage again to a very small percent. 0.1% was good enough. 0.1%, that's good enough. So it's done. Okay, now we need to multiply these two signals. So let's break down this connection. We will use the scope at the end, so let the scope be. Again, fetch the product block, and you can find the product block in math operations. The product block is here. Just drag and drop. Okay. It has already 2 ports, you need 2, so nothing to worry about here. First connection done. Second connection is already done. The output should go into the scope. Okay. So let's, without any delay, let's simulate this thing. Let's see what happens. So our sampling is done. Let's see the sample signal. You can see the sample signal is here. We are taking samples at certain time intervals, and this is the output. If you see, you will readily recognize that this doesn't look a lot like a sine wave, because our sampling frequency was not that high. It was just equal to the Nyquist theorem. It's not that high, so your naked eye cannot actually visualize that. This is a sampled signal of a continuous sine wave. Okay, so let's try to visualize it more. If we want to visualize it a bit more, we want to increase the frequency of the sampling signal. That means we need to decrease the time period of the pulse train. Let's bring one more scope for better visualization. Scope. I will use this scope to visualize this pulse train. So if I just visualize it now, this is our pulse train. We have one impulse every 0.001 second. We need to increase the frequency. Increasing the frequency will decrease the time period, so we want to decrease the time period. Let's decrease it by 2 times. So instead of 0.001, we will now 0.0005. Let's simulate it. Let's visualize it. Now you can see, previously there were only one impulse in every 0.001 second. Now we have 2, 1, 2, and then again the next period. In the next 0.001 second we have another 2, 1, 2. So we have increased the frequency and doubled it actually. So let's see how our sample signal has turned out. It is still not a very good signal to visualize, so let's increase the frequency a bit more. Now we have increased the frequency by 10 times of Nyquist frequency. Now you can get a very good visualization that this was actually a sine wave in continuous form. See, you have sort of continuous wave. Let's see how many samples are there. Let's say 0, or let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Almost 10 signals in the half cycle. This actually corresponds with our calculation well, because if there are 10 samples in the half cycle, in the complete cycle you will have 20 samples. And actually, if you follow the Nyquist theorem, you will have 2 samples per period. I am repeating, if you follow the Nyquist theorem, there will be 2 samples per period. We are actually doing this at 10 times of the Nyquist frequency. So it will be 10 multiplied by 2 or 20 samples. So our theoretical calculation and our understanding actually matches. I am again repeating this part. If you follow Nyquist theorem, you will have 2 samples per period. We are doing it in a frequency of 10 times compared to the Nyquist rate. So we will have 2 multiplied by 10 samples or 20 samples by theoretical calculation, and in the graph we can see there are 10 samples in the half cycle, so in the complete cycle we will have 20 samples. So this matches. If you just increase the frequency even more, you need to decrease. Let's do it another. So now we are doing it at 100 times of the Nyquist frequency. So this time our impulse train will be very So here is our impulse train. You can see they are in very close proximity. All the impulses are in close proximity, so you cannot just differentiate them in the naked eye. So let's check the output. You can see the output is also actually similar to a sine wave, because there are so many close impulses in close proximity, right? So you get the idea. The more you increase the frequency of the sampling signal, the more samples you get, and more closely it resembles to the original signal. But for the complete reconstruction, we need at least Nyquist frequency. If you don't take Nyquist frequency, then your sampling process will not actually correlate with the original signal. So let's do something. Let's just change the frequency and make it less than the Nyquist. Let's make the sampling frequency equal to the continuous signal frequency. So it will be 0.005. I have to check back. Oh, it should be 0.002. I'm sorry. So now our sampling frequency and our original signal frequency are same. So let's check it. Yes, we have only 5 samples in 0.01 second. So only 5 samples. So it's similar. Let's see the sample signal. You can see in this case, in this particular case, sample signal doesn't correspond to the continuous signal at all. You can see from this sampled signal, you can never say that this came from a sine wave. Never. Even by naked eye, you cannot say this has even a slight possibility of coming from a sine wave. No possibility at all. But if you keep this at least twice the original signal, if you keep it at least 0.001, at least this is the Nyquist rate, you can actually feel a bit of resemblance with the original signal. You can see it is not perfect, but you can, if I tell you that this came from a sine wave, you would actually believe, because if you just have a good imagination, you can see that this signal was hovering in this direction, right? Right? Yeah. If I just draw it for you. So you can, if you have a good imagination, you can actually understand that this came in this fashion. So there was a signal like this here. So you were taking samples at this time intervals, right? So it's possible. But the signal I showed you earlier, there were no chance that anyone would say that came from a continuous sine wave. So I have tried to discuss this in very detail. I have tried to show you the effect of every sampling frequency equal to Nyquist rate, higher than Nyquist rate, and lower than Nyquist rate. If it is lower than Nyquist rate, then there is no chance that we are getting back the original signal. So it should be at least Nyquist. If it is equal to Nyquist, then we get 2 samples per period. It is very difficult to visualize, but if I ask you to visualize with a imagination or great imagination, you can actually think that it came from the continuous sine wave. That's fine. But if we increase the frequency to 10 times or 100 times of the Nyquist frequency, then there was a proper visualization that yes, this actually came from the continuous sine wave. So that was all for the sampling experiment. For the report, you will have to reconstruct the original signal from the sample signal. Okay, this is 10 times of Nyquist rate. So the last time I was holding it. So this is our input signal, input sample signal. In the reconstruction part, you will have to reconstruct the continuous sine wave from this sample signal. So how to do it? I have already mentioned it in my videos, that I am just mentioning it again for your better understanding. In the frequency domain, sampling means actually repetition of the spectrum. So this is our original spectrum. It will be repeated. And it goes on. But we need only this spectrum. We don't need these things. So what we need to do is we need to cut these spectrums off. cut it off, cut it off, cut it off, cut it off. But cutting off is not this easy for Simulink. What will you need to do is we need something that will filter only this thing out. That is a low pass filter. You need a low pass filter which is something like this. Multiply them. Here it is 1. So this, in this portion you will get the output as equal to the input, and in this portion it is 0, so you will not get anything. So this is our reconstruction. Reconstruction in frequency domain. This reconstruction in frequency domain is enough for retrieving the time domain signal. So the important thing is you have to choose this low pass filter correctly. There are already a low pass filter LPF block in analog filters. You have already used low pass filter. I am not going into the detail of how to find it. Analog filters, you can choose a low pass filter. There are two parameters. The first one is the filter order, and the next one is the filter cutoff frequency. Cutoff. You have to experiment with these two. Cutoff frequency, you can see that cutoff frequency should be equal to the message frequency. You can see. You can adjust it a bit more. You can do something slightly greater than the message frequency. And the order is by default, I guess it was by default 8 or 4, I don't remember actually. You have to experiment this with order 2. Try different orders. Try order 1, try order 2, try order 3, try order 16, and see how these orders are actually helping you to reconstruct the original signal closely related to the main signal. So I am not doing this for you. It is your task to complete in the report. So that's all for this experiment. I hope you have got a firm understanding of how to do the sampling using Simulink, and also got some basic idea of how to reconstruct the original signal. So your original signal should look something like, if I just take back the scope, your original signal should look something like this. Oops. If you when you reconstruct the signal, the reconstructed signal should look something like this. It will not be accurately this signal. There's a lot of non-realities, but your signal should look something like this signal with proper time period. The time period here is 0.002. One full cycle takes 0.002 seconds. Your reconstructed signal should have the same period. If the period is not matched, then it's not, you are not doing it right. So these are the things. That's all for this experiment. Hope you enjoyed. Let's meet in our live class and discuss more about it. Thank you.